You probably think your newer appliances, vehicles, and devices are better because they use less energy, lower bills, smaller footprint, less waste. That's the promise. But then something strange starts happening. Your high-efficiency washer breaks after 3 years. Your new fridge runs hotter than the old one ever did. Your smart HVAC system needs a technician just to reset it. And the repair bill? It's often so high you're told to just replace the whole thing. So what changed? Because this isn't random. It's not bad luck. And it's not just modern products being worse. There's a hidden mechanism behind all of this. One almost nobody explains. Efficiency didn't just improve performance. It fundamentally changed how these systems are designed. And in the process, it introduced something far more dangerous than inefficiency ever was: fragility under stress. The more efficient something becomes, the closer it operates to its limits. Less margin, less tolerance. More heat, more pressure, more complexity packed into tighter spaces. It's like buying a car where the engine is designed to run at redline all the time. It performs well on paper, but it has no room to breathe. And eventually, something gives. This is the energy efficiency trade-off nobody talks about. And once you see it, you start noticing it everywhere. Problem number 1 is heat, not obvious heat. Not the kind you feel when you open a machine. The kind that builds slowly, invisibly, inside components that were never meant to run this hard, this often. The mechanism is simple, but rarely explained. To hit efficiency targets, manufacturers reduce energy input, but the output expectations don't change. So systems compensate by running longer. And longer run times mean sustained heat exposure across every internal part. Take modern dishwashers. Older models blasted hot water, finished quickly, and shut off. They used more energy, but they gave components time to cool down. New models stretch that same job across 2 or 3 hours. Lower power draw, but constant operation and constant heat cycling. The evidence is everywhere. Pumps wear out faster. Control boards fail from thermal stress. Seals degrade sooner because they're exposed to longer cycles instead of short bursts. The common belief is that newer machines are just cheaper. But that's not the full picture. They're stressed differently, designed to operate in a narrower thermal window. And when something shifts slightly outside that window, failure accelerates. The consequence for you is subtle at first. Longer cycles, slight performance drops. Then one day, it stops working entirely, and the failure feels sudden. But it isn't. It's been building for hundreds of hours of continuous microstress. Ask technicians about this, and many will tell you the same thing quietly. It's not that parts are always worse. It's that they're being pushed harder for longer than they used to be. Problem number 2 is miniaturization. To improve efficiency, manufacturers shrink components, smaller motors, thinner wiring, more compact circuit boards, less material, less resistance, better efficiency ratings. But smaller parts have a hidden weakness. They hold less heat, they dissipate less energy, and they fail faster under stress. It's like replacing a thick steel beam with a lighter one that technically meets the load requirement. It works until something unexpected happens, and then it fails instantly instead of gradually. The mechanism here is density. Modern systems pack more functionality into tighter spaces. Electronics, sensors, and power components all sit closer together, and when heat builds up, there's nowhere for it to go. The evidence shows up in common failures. Burned control boards, melted connectors, capacitors that bulge or leak after just a few years. The common misbelief is that electronics are unreliable, but the deeper truth is that they're operating in harsher internal environments than ever before. The consequence is catastrophic failure instead of gradual wear. Older systems gave you warning signs like noise, reduced performance, and visible wear. New systems often fail instantly. One day they work, the next day they're dead. And here's the part most people don't realize. Miniaturization doesn't just make things smaller. It removes repairability. Components are soldered tightly, modules are sealed, and access points are eliminated. So even if one small part fails, the entire system often has to be replaced. Around this point, if you've ever had something fail way earlier than expected, you've already experienced this trade-off firsthand. Drop a comment with what broke and how long it lasted, because the next layer goes even deeper. Problem number 3 is software-controlled efficiency. This is where things shift from physical design to system-level decisions. Modern appliances don't just run, they optimize. Sensors adjust cycles in real time. Algorithms reduce energy usage dynamically. Systems throttle performance to meet efficiency standards under test conditions. On paper, it's brilliant. In reality, it introduces a new failure point. Software becomes part of the machine's core function. The mechanism is control dependency. Instead of a simple mechanical system doing one job reliably, you now have a network of sensors, logic boards, and firmware all coordinating to achieve efficiency targets. And if any one part of that chain fails, the entire system can shut down. The evidence is everywhere. Washing machines that won't spin because of a sensor error. HVAC systems that lock out due to software faults. Refrigerators that stop cooling because a control board misreads temperature data. The common belief is that these failures are random glitches, but they're not. They're a direct result of adding layers of control to optimize energy use. The consequence is loss of simplicity, and with that, loss of resilience. Older systems were inefficient, but they were tolerant. You could bypass a switch, replace a single part, and keep it running. Modern systems are precise, and precision systems fail when conditions aren't perfect. Even technicians will tell you this off the record. Diagnosis now often starts with software, not hardware, and replacement means swapping entire modules instead of fixing individual components. Problem number 4 is regulatory pressure. This is the system-level force driving everything you've just heard. Energy standards don't just encourage efficiency, they enforce it. Manufacturers are required to meet specific benchmarks under controlled testing conditions. And here's the hidden mechanism most people never see. Products are often optimized to pass the test, not to perform reliably over time. It's like studying just enough to pass an exam without actually understanding the material. The mechanism is test-based design. Engineers design systems that hit efficiency targets during standardized cycles, but real-world usage is far messier. Longer run times, heavier loads, different environments, and under those conditions, the system experiences more stress than it was optimized for. The evidence shows up in mismatched expectations. A dishwasher that technically meets efficiency ratings but struggles with real cleaning performance. A heat pump that works perfectly in mild conditions but struggles in extreme temperatures. The common belief is that regulations made products better, and in some ways they did, but they also forced designs into tighter margins. The consequence is a system that performs well in controlled scenarios but degrades faster in real life. And manufacturers know this. Not openly, but internally, it's understood that hitting the rating matters more than long-term durability. If you're still with me, this is where it gets even more important. Hit like and subscribe if you want more breakdowns like this. Because once you start seeing these patterns, you can't unsee them. Now here's the force multiplier. Everything we've talked about leads to one unavoidable outcome: shorter functional lifespan. Not because things are designed to fail immediately, but because they're designed to operate with almost no margin for error. Every component is working harder, longer, and closer to its limit. And when even a small variable changes, like heat, load, or voltage fluctuation, the system doesn't adapt. It breaks. And here's the final insight that reframes everything. Efficiency is not free. It always comes from somewhere. In older systems, inefficiency was absorbed as excess capacity, thicker materials, and simpler designs. In modern systems, that buffer has been stripped away. What you gain in efficiency, you often lose in durability, repairability, and control. And once you understand that, you start making different choices. You stop assuming newer is better. You start asking how something achieves its efficiency, not just whether it does. And you begin to notice that the products that last the longest are often the ones that aren't chasing the absolute edge of efficiency. They leave room to breathe.